In this lesson, you will learn about infinite limits. First up, behavior of graphs and infinite limits. Consider the graph of f of x equals 1 over x, which we know looks like this. We know that if we try to plug in x equals 0, that f of x does not exist. And now let's explore what happens to f of x as the x values approach 0 from the left. So we're talking about x values coming in this way. When x is negative 0.1, f of x is negative 10. If we get a little closer, where x is negative 0.01, then we see f of x goes to negative 100. And if we get closer at negative 0.001, f of x goes to negative 1,000. So we can see that as the x values get closer and closer to 0 from the left, the y values are getting more and more negative, so large magnitude negative numbers. Now, if we analyze the behavior of the graph there, as x approaches 0 from the left, we can see our y values are heading off towards negative infinity. So as x goes to 0 from the left, f of x goes to negative infinity. And we see that both by looking at the graph and by plugging in actual x values and finding the y values. So as x approaches 0 from the left, we see that f of x is heading off to negative infinity. Another way of saying that, here, as x approaches 0 from the left, 1 over x goes to 1 over 0 minus, which we see is heading off to negative infinity. Now let's look back at the graph and plug in values for x that are approaching 0 from the right. So if we put in 0.1 for x, the y value becomes 10. And as we get closer to 0, at 0.01, the y value is 100. And at 0.001, the y value is 1,000. And now that is easy to see on the graph. As x gets closer and closer to 0 from the right, the y values are heading up here. So we can say as x goes to 0 from the right, f of x is heading off to positive infinity. So when we analyze that, as x goes to 0 from the right, 1 over x is going to 1 over 0 from the right, which we just discovered is going to infinity. Next, we consider the graph of f of x equals negative 1 over x. We know this negative sign just means the graph is going to flip over the x-axis, so it will look like this. As we plug in values for x that come into 0 from the left, we see that the y values get bigger and bigger. So looking at the graph, as x approaches 0 from the left, the y values are heading up here to positive infinity. So x goes to 0 from the left, f of x goes to infinity. So we can fill that in on the chart. And then that means here, as x approaches 0 from the left, negative 1 over x is going to negative 1 over 0 minus, which we've just discovered means it goes to positive infinity. Now, comparing that to what happens to the y values as x approaches 0 from the right, we see the y values are getting to be larger and larger magnitude in the negative direction. So looking at the graph, as x comes into 0 from the right, the y values are heading off to negative infinity here. So x approaches 0 from the right, f of x is approaching negative infinity. So let's fill that in. And as we analyze that behavior, we say as x approaches 0 from the right, negative 1 over x means we have negative 1 over 0 plus, and we just discovered that goes to negative infinity. So now let's summarize what we just learned about infinite limits. If we have the limit as x goes to 0 from the left of 1 over x, that turns into 1 over 0 minus, which we found out was negative infinity. Whereas if we had the limit as x approaches 0 from the right of 1 over x, that turns into 1 over 0 plus, coming in from the right, which was positive infinity. When we had the limit as x approaches 0 from the left of negative 1 over x, which is negative 1 over 0 minus, that went to positive infinity. And finally, when we had limit as x approaches 0 from the right of negative 1 over x, that was equal to negative 1 over 0 plus, which we found out was negative infinity. So you notice that if you have 1 over a tiny negative, that's negative infinity. So the rules about dividing a positive by a negative apply, and our result is negative. Whereas here, if we have a positive divided by a tiny positive, that result is positive infinity. Here, if we have a negative divided by a tiny negative, a negative over a negative is a positive. That's why that works out to be positive infinity. And likewise here, if you have a negative over a tiny positive, the result will be negative, and that's negative infinity. Now, in all cases, a limit going to infinity or negative infinity means the limit does not exist. Remember that for a limit to exist, that limit must equal a finite number. It can't be infinite. So infinite limits are limits that also do not exist. It's just that we now know the way that they don't exist. We know that they don't exist either going in the negative infinity direction, like these two, or they don't exist by going to the positive infinity direction. In this example, evaluate each limit from the graph. We are given this graph of y equals g of x. First, we must find the limit as x approaches negative 2 from the left of g of x. As x comes into negative 2 from the left, we can see that the y values of the function are approaching positive infinity. So that means this limit is positive infinity. The limit as x approaches negative 2 from the right of g of x, coming into negative 2 from the right, the y values are heading down to negative infinity. So that means the limit is negative infinity. And then the two-sided limit as x approaches negative 2 of g of x, since these two values are different, and in fact they both don't exist, this is a DNE. this limit does not exist. Now the limit as x approaches 1 from the left of g of x, so we're coming into 1 from the left, the y values are heading up to positive infinity, so that's that limit. The limit as x approaches 1 from the right of g of x, we're coming in this way, so the y values are going off to infinity. And in this case, because the limit as x approaches 1 from the left and as x approaches 1 from the right are both going to infinity, we can say that the two-sided limit as x approaches 1 of g of x is also infinity. But remember, that still means it does not exist. All of these limits do not exist because they're infinite. It's just that we know how they don't exist. And something important to notice here is when we have infinite limits, take a look at what's happening at the graph. As the y values go to either infinity or negative infinity, this is occurring at vertical asymptotes on the graph. In this section, you will learn about vertical asymptotes. First up, a quick algebra review for vertical asymptotes of a rational function. The function h of x equals f of x over g of x will have a vertical asymptote at x equals c whenever the following conditions exist. We need the denominator, g of c, to equal 0, but it must also be true that the numerator, f of c, does not equal 0. So we look for vertical asymptotes whenever the denominator of the rational function is 0, but we have to verify that the numerator does not equal 0 at that point. Now we will learn the calculus definition of vertical asymptote. The line x equals c is a vertical asymptote of f of x if either of these one-sided limits occurs. If the limit as x approaches c from the left of f of x is either positive or negative infinity, or if the limit as x approaches c from the right of f of x is positive or negative infinity. Now, one thing to be extra careful of when you are applying the definition of vertical asymptote is that you must perform a one-sided limit to do the test. And also notice that it's not sufficient to show that the limit does not exist. You have to show that that one-sided limit is either positive or negative infinity. And we will use this algebra concept for when the denominator is 0 and the numerator is not, so that we know where to look for the vertical asymptotes. So let's see how this will work. In this example, apply the definition of vertical asymptotes to find the location of any vertical asymptotes or removable discontinuities. G of x is equal to the quantity 2x squared minus 7x minus 4 over the quantity x squared minus 16. Now we know that vertical asymptotes can occur when the denominator is equal to 0, and of course we also need the numerator to not be 0 at that location. So let's first factor both the numerator and the denominator. So pause the video, factor the numerator and denominator, then restart the video, when you're ready to check your factoring. The numerator is going to factor into 2x plus 1 times the quantity x minus 4, and the denominator is the difference of squares, so that's quantity x plus 4 times quantity x minus 4. Now, the denominator is equal to 0 at -4 and 4. So those are the potential locations of vertical asymptotes or removable discontinuities. So we will apply the definition of vertical asymptotes at both of those values to see what happens. So first, let's look at x equals -4. Now bring up the definition of vertical asymptotes, and remember that we have to perform a one-sided limit, and we have to see if that limit goes to positive or negative infinity. Now we can do either a left-sided limit or a right-sided limit. It doesn't matter. So maybe we will do the limit as x approaches -4 from the right, and we have 2x plus 1 times x minus 4 in the numerator over x plus 4, x minus 4 in the denominator. Now, in evaluating this limit, we know that we can cancel out the common factor. This is now the limit as x approaches -4 from the right of 2x plus 1 over x plus 4. Now if we try direct substitution, we put the -4 in for the x, the numerator becomes -7, and the denominator is 0. But remember, this is a one-sided limit, so we have to figure out whether it's 0 plus or 0 minus in order to know whether this goes to infinity or negative infinity. So if we make a little number line here and put -4, if we are coming in from the right, that means we can think -3.9999999 going on forever. And if we were to take that value, and remember, this is just a temporary substitution, plug it in for x, we see that we would get a tiny little positive number. And now we know that a -7 over 0 plus, that's going to go to negative infinity. And because our one-sided limit went to negative infinity, we can say, therefore, x equals -4 is a vertical asymptote. Next, let's look at what happens at +4, which also makes the denominator 0. So now we will look at x equals 4. And once again, if we apply the definition of vertical asymptotes, we know we have to perform a one-sided limit, and that limit would need to be infinity or negative infinity to result in a vertical asymptote. So if we do the limit as x approaches 4, and we can do the right or the left, maybe this time we'll come in from the left, we have 2x plus 1 times x minus 4 in the numerator over x plus 4, times x minus 4 in the denominator. And of course, inside of the limit, we are allowed to cancel the common factors. So this becomes the limit as x approaches 4 from the left of 2x plus 1 over x plus 4. And now this time, when we do direct substitution, we see that the numerator becomes 8 plus 1, which is 9. And the denominator becomes 4 plus 4, which is 8. Since the one-sided limit was not positive or negative infinity, that means that x equals 4 is not a vertical asymptote. And in fact, what this means is that G has a removable discontinuity at x equals 4. And this all makes sense. First, because by the definition of vertical asymptote, we did not get an infinite limit. And second, if we apply that rule from algebra that tells us that vertical asymptotes occur when the denominator is 0 but the numerator is not, we can see that at x equals 4, both the numerator and the denominator are going to be 0 there. 0 over 0 is not a vertical asymptote. It's only when the one-sided limit works out to be infinite that we get a vertical asymptote. When the one-sided limit works out to be finite, that will not be an asymptote. And in fact, we learned in the definition of continuity, when the limit exists, we're going to get a removable discontinuity at that x value. In this example, apply the definition of vertical asymptotes to find the location of any vertical asymptotes or removable discontinuities. F of x is equal to sine of x over the quantity x squared minus 3x. Now we know we are interested in the places where the denominator will be 0. So let's factor this denominator. Of course, the numerator is sine of x, and the denominator will be x times the quantity x minus 3. So this denominator will equal 0 whenever x is 0 or x is 3. So let's first look at x equals 0. Now, according to the definition of vertical asymptotes, we have to do a one-sided limit and find out if that limit goes to infinity or negative infinity. We can either do a right-handed limit or a left-handed limit. It doesn't matter. So let's do limit as x approaches 0 from the right, and we have sine of x over x times the quantity x minus 3. Now, if we just tried to do direct substitution, the sine of 0 equals 0, and if we plugged in 0 for x here, 0 over 0 is indeterminate. So that tells us we will have to do some work on this limit in order to find it. So we can rewrite this as the limit as x goes to 0 from the right of sine of x over x times the limit as x goes to 0 from the right of 1 over x minus 3. Remember earlier in this chapter we learned that you can take the limit of a product and write it as the product of the limits. So now both of these can be evaluated. We learned a special limit, that the limit as x approaches 0 of sine of x over x is equal to 1. Now, if that two-sided limit is equal to 1, then that means both of the one-sided limits are equal to 1. So therefore, the limit as x approaches 0 from the right of sine of x over x is also equal to 1. And the limit as x approaches 0 from the right of 1 over x minus 3 is just going to be negative 1/3. And notice that we don't have to concern ourselves here with whether we are approaching negative 1/3 from the left or from the right. Either way, it's still approaching negative 1/3. It's only when we get a 0 that we have to know 0 from the right or 0 from the left, because that changes whether we have a negative number or a positive number. But whether we're approaching negative 1/3 from the left or from the right, it's still just negative 1/3. So this limit just equals negative 1/3. And that tells us that x equals 0 is not a vertical asymptote. And in fact, it means that f has a removable discontinuity at x equals 0. Now we also need to look at x equals 3, because that was the other place that made the denominator 0. So according to the definition of vertical asymptotes, we have to do a one-sided limit. So we can do the limit as x approaches 3 from the right. We also could do from the left. It doesn't matter. We have sine of x over x times the quantity x minus 3. Now, if we try direct substitution here, we would get the sine of 3 over 3. And remember, we don't have to concern ourselves with whether this is 3 from the right or 3 from the left here, because either way, it's just approaching a positive 3. If this were a 0, we would have to concern ourselves whether it was 0 plus or 0 minus. However, now here, when we plug the 3 from the right into quantity x minus 3, now we get a 0. We need to determine if it's 0 plus or 0 minus. So let's make a little number line here. We're going to put on 3 because that's what we're approaching. If we are coming into 3 from the right, that means we think 3.00000001, infinitely close to 3 from the right. And if we take that value and plug it in and subtract 3, we would get a tiny little positive number. Now, what we have to do to figure out what this equals, we need to know whether this number, sine of 3, is positive or negative. And so for that, we can think about the unit circle. we know this would be 0. This is pi over 2, which is approximately 1.57. This is pi, which is approximately 3.14. So then an angle of 3 is going to live here. And we know that in quadrant 2, sine is positive. So that means that sine of 3 is a positive number. So we have a positive in the numerator, a positive 3 in the denominator, and this 0 plus, which tells us that's going to go to positive infinity. Because our one-sided limit went to infinity, therefore x equals 3 is a vertical asymptote. Next up, we go over some properties of infinite limits. Let C, L, and K be real numbers with L greater than 0 and K greater than 0. So those two are positive. And let F and G be functions with the following limits. The limit as x approaches C of f of x is equal to infinity. The limit as x approaches C of g of x is equal to L, and the limit as x approaches C of h of x is equal to negative k. So remember that L and k are positive numbers, so then this limit is a positive value, then the opposite of k would be a negative value. First, we look at the limit as x approaches C of the sum f of x plus g of x. And we can write that as the limit as x approaches C of f of x plus the limit as x approaches C of g of x. So then we can substitute in. We know this limit is equal to infinity plus this limit is equal to L, and infinity plus any finite positive number is going to equal infinity. Here we have the limit as x approaches C of the product f of x times g of x. So we can write this as limit x approaches C of f of x times the limit as x approaches C of g of x. This first limit we already know is infinity, and we have to take that times this second limit, which is this positive number L, and infinity times a positive number is just infinity. Here we have the limit as x approaches C of the product f of x times h of x. So that will be the limit as x approaches C of f of x times the limit as x approaches C of h of x. This first limit we know is infinity, and this second limit we know is negative k, and infinity times a negative number just gives us negative infinity. And lastly, the limit as x approaches c of the quotient g of x over f of x will be the limit as x approaches c of g of x over the limit as x approaches c of f of x. Now, filling in these values, we know the limit as x approaches c of g of x is equal to L over the limit as x approaches c of f of x is infinity, and any finite number divided by infinity is going to go right to 0. And this would be true even if L was a negative number. A finite negative number divided by infinity is going to go to 0. It would also be true if this was negative infinity in the denominator. A finite number divided by negative infinity is also going to be 0. It's just going to go through negative numbers if the numerator is positive. Similarly, in this first property, if this had been f of x minus g of x, then of course this would have been a minus sign, and then this would have been a minus sign. The result would still be infinity, because infinity minus a finite number is still infinity. And now we will use these properties of infinite limits and take a look at some examples. In this example, evaluate each limit. First up, we have the limit as x approaches 2 from the right of 1 over the quantity 2 minus x. Now, if we do a direct substitution here, we see that we will get 1 over 2 minus 2, which is 0. But remember, because we have 2 coming in from the right, we have to think about what 2 minus 2 coming in from the right will equal. So let's make a little number line and put a 2 on there. Now, if we're coming in from the right of 2, then you would think 2.0000, infinitely many zeros, 1. And that's what you're putting in for this x value. So then 2 minus a number that's slightly bigger than 2, that's going to result in a tiny little negative number. And we know that 1 over 0 minus is negative infinity. Next up, we have the limit as x approaches 1 from the left of quantity x plus 1 over quantity x squared minus 5 times quantity x minus 1 in the denominator. So let's plug these values in. If we put 1 plus 1 in the numerator, that's a 2. And remember, because it's not a 0, we don't have to worry about whether we're approaching 2 from the right or left here. It's a positive 2 no matter which way we're going after it. And that's going to be over here. If we put the 1 in, we have 1 squared is 1 minus 5 gives us a negative 4. And it doesn't matter whether it's approaching negative 4 from the right or from the left. It's going to always be negative 4. Whereas when we take the 1 coming in from the left and plug it in here, we are going to get 0. And this is where we need to decide whether we have 0 plus or 0 minus. So we make the number line, we put 1, and if we are approaching 1 from the left, what we are going to think is 0.9999999, as many nines as you can handle. If we take that number temporarily and plug it in and subtract 1, we see that we are going to get a tiny little negative value. So now we have a positive in the numerator, 2 negatives in the denominator. So our result is going to be a positive number, and because we have that 0 minus in the denominator, this is going to infinity. Next up, we have the limit as x approaches -2 from the left of the quantity -3 plus 5 over the quantity x plus 2 squared. So we can substitute directly, and we will have -3 plus 5 over. Now, if we put a -2 into this quantity, we are going to get a 0, but we will need to decide if we're going to get 0 plus or 0 minus. So let's make a number line, put -2 on there. We know that we are coming into -2 from the left, so we have to think -2.000001. Now if we take that number, plug it in for x, then this quantity becomes a tiny little negative, which we have to square. So this becomes -3 plus 5 over 0 plus, because when we square that negative, it becomes a positive. This equals -3 plus infinity, which is going to equal positive infinity. In this example, we have to evaluate the limit as x approaches -1 from the right of the quantity x times quantity x plus 2 over quantity x plus 1. So let's go ahead and do a direct substitution. Plugging in here, we are going to get -1. We don't care if it's -1 from the right or left, because no matter what, it'll still be -1. Then here, get the fraction bar. If we put -1 into this numerator, add 2, and we get +1. Put -1 into the denominator, and we are going to get 0. So that means we need to determine whether it's 0 plus or 0 minus. Let's make the number line, put a -1 on there, and we will be coming in to -1 from the right. So that means we are thinking -0.9999999, on and on and on. Now when we take that, plug it in for x, and add 1, that means that we are going to get a tiny little positive number. Then this is going to equal -1 times positive infinity, which is equal to negative infinity. In this example, we have to do the limit as x approaches pi from the right of the quantity 3 plus 2 cosine x over sine of x. So if we do the direct substitution, we will get 3 plus 2 times the cosine of pi, and the cosine of pi is -1, over, in the denominator, we know that the sine of pi is 0, and we are going to need to determine whether it's going to be 0 plus or 0 minus. Now what can help us is to look at the graph of sine. We know the period is 2 pi, so that means halfway is pi. The quarter point is pi over 2, 3/4 point, 3 pi over 2. And we know that the graph of sine starts at 0 and then goes to 1. Then it goes back down to 0, then to -1, and then back up to 0. Now, as we are approaching pi coming in from the right, that means we are on this part of the graph because we have to be coming into pi from the right. Well, you can see that the y value is approaching 0, but it's coming in through negative numbers. So this denominator is 0 minus. Now this is equal to 3 minus 2 in the numerator, which is 1, over 0 minus, and this is going to go to -infinity. Here we have to evaluate the limit as x approaches pi over 2 from the left of the quantity x plus pi over cosine x. It's time to check your understanding. So pause the video, try this one on your own, then restart when you're ready to check your answer. Let's get the fraction bar. In the numerator, we have to do pi over 2 plus pi. So pi over 2 plus 2 pi over 2 is 3 pi over 2. In the denominator, we have to do the cosine of pi over 2 coming in from the left. Now we know the cosine of pi over 2 is 0, and we will need to determine whether it's 0 plus or 0 minus. So once again, let's use the graph. We know the period is 2 pi, so half of that is pi. The quarter point is pi over 2. The 3/4 point is 3 pi over 2. We know the min will be at -1 and the max at 1. So cosine of x starts at 1, goes to 0, to -1, to 0, back to 1. Now remember, we are approaching pi over 2 from the left, which means we will be on this part of the graph. The y value is approaching 0 through positive numbers. So this is going to be 0 plus, and 3 pi over 2 over 0 plus is going to go to positive infinity.